In this video, we will solve multiple problems from Chapter 2, Kinematics of Particles. So what I'm going to do is I'm going to pick a couple of examples from the Cartesian coordinate system. I will also pick an example from tangent normal and another from polar coordinate system. And finally, I'll conclude this video with an example from multiple particle system where we will try to relate the motion of various particles. So let's start with example 2.2. So whenever I say example EX 2.2, that essentially means that it's actually a solved example. Okay, so example 2.2 is a solved example in your textbook. If I say problem P something, then it's an unsolved problem from the textbook. So let's read this problem. Ship B tracks an unmanned aerial vehicle P launched from A. So this is the ship P that's tracking, and this is the A is the unmanned aerial vehicle. And flying parallel to the water for the first 8 seconds of flight, the recorded motion of P is given as this. So let's start by writing given. So given is delta T as 8 seconds. And then position of particle P is given as 225 plus 2.15 q I hat and this is in meters. Okay, where T is in seconds. Determine A, the trajectory of P for 0 to 5 seconds, the velocity and speed of P, the acceleration of P, and its orientation related to the path. So there are three things that are being asked for. Okay, so what would be the trajectory? Well, trajectory is going to be maybe some sort of curved path. So the question is, what is that equation? So something like y equal to x squared, or y equal to x if it was a line or something like that, right? Okay, so what do we know? We know that this is the trajectory for first 8 seconds. Okay, so what is this telling you? This is telling you the x position of the particle P, and this is telling the y position of the particle P. So let's write this as xt equal to 225 plus 2.15 t cube, and y sub t, yt equal to 225 plus 0.993 t cube. So if I want to get a relationship between x and y, which would give me the path or the trajectory of P, all I have to do is get rid of the t from here. And now in both equations, we have t cubed, so it's actually an easy thing to get rid of the t cube, right? So what I can do is I can write t cubed from here, okay? So I will read, let's say this is equation 1, this is equation 2. So from 1, I can write t cubed equal to x minus 225 over 2.15, and then I can substitute this in 2, right? So y would be equal to 225 plus 0.993, and t cube is x minus 225 over 2.15, and that gives you basically the path. And you can clearly see this is actually going to be a line, right? Because both at y and x over here are linear terms. So that's your trajectory, that's your path. So that's solution to part A. Okay, let's look at the velocity and speed of P. So that's part B. We already know the position vector, so we can write the velocity directly from that. So velocity is equal to d over dt of r as a function of time, and that would be, so I'm just going to differentiate it directly, that will be 2.13 times 3t squared I hat plus 0.993 times 3t squared j hat, and this would be in meters per second. Okay, so that's the velocity. What's the speed? Well, the speed of v is nothing but the magnitude of v, and that would be square root of 2.13 times 3t squared whole square plus 0.993 times 3t squared whole square, and that would be in meters per second. So if you are looking for a magnitude of the velocity or the speed at any certain instant, you can substitute for the value of the t in this expression and get that. What about part C, the acceleration of P? So let's write the acceleration. Acceleration of P would be d over dt of velocity of P. So this is velocity of P. So let's differentiate this once more, and we'll get 2.13 times 6t I hat plus 0.993 times 6t j hat meters per second squared. And that's the acceleration expression. Again, you can see that because we have the function of time here, acceleration is actually not constant. The last part of the C is orientation related to the path. Okay, so we're looking for the direction, right? The orientation of the acceleration of P related to the path. So how do we get that? Well, what is the direction of the path? Direction of the path would be tangent to the velocity, right? Oh, I should say the other way. The velocity is tangent to the path, right? So if we are looking for this orientation related to the path, what I have to do is take the dot product between acceleration and velocity, right? So if I have two vectors A and vector B, and I'm looking for the angle between the two, I can easily obtain it. In this case, velocity of P is tangent to the path, right? That's VP, and acceleration could be, let's say, pointing this way, and we are looking for its orientation of acceleration with respect to the trajectory, right? With respect to the path. So AP dot VP, AP is known, VP is known. So this would be equal to magnitude of A, magnitude of V times the angle between the two. So you take the dot product on the left hand side, you write the magnitude of acceleration, you write the magnitude of velocity, and that would give you cosine of the theta. You do a cosine inverse, and that would give you theta from that. Okay. Example 2.4 is acceleration as a function of time. This is also a solved example in your textbook. So in this question, there is a rocket sled that accelerates from rest along a straight rail. So what is given to us? Let's start by writing that. So given is that its initial velocity is 0 because starting from rest, and it's moving along a straight line path. The sled's acceleration is beta t squared. So acceleration is given as beta t squared. Clearly, this is not constant. So let me write that non-constant. Just to remind ourselves that we shouldn't be using Galileo's equation in this case, where beta is a constant and t is time in seconds. The sled achieves a final speed Vf equal to 180 miles per hour. So Vf is equal to 180 mph. Okay, even though this is not a very standard way of writing miles per hour. After traveling a distance d equal to 300 feet. So it travels 300 feet in that time period. So it goes from 0 to 180 miles per hour and it travels a distance of 300 feet. So the question is determine beta and the time required to achieve Vf. Okay, so find beta and t that it takes to go from 0 to, let me say, V0 to Vf, right? V0 happens to be 0 over here. Okay, so clearly this is a problem where the choice of the coordinate system is fairly straightforward. It's Cartesian coordinate system, it's moving along a straight line path, right? So we could say, okay, this is my frame over here. That's my positive x direction, all right? And I will indicate the position of this with, let's say, simply x, all right? So no problem with that. So where is our starting point? Well, the starting point would be with the acceleration, right? The acceleration we know is defined as dv over dt, and acceleration is given as a function of time. So this can be easily integrated. So I'll take b dt squared here and dt on this side, and integrate it from v0 to vf, time changing from 0 to t. Beta is constant, so this is simply t cubed over 3, and we get vf minus v0 equal to beta t cubed over 3. Okay, so now from this relationship, let's call it number 1. From this relationship, can we determine everything that is asked for? We know Vf, we know V0, we don't know what beta is, and we don't know what time is, right? So there are two unknowns over here in this equation. So we clearly can solve for both beta as well as t from this. So we need something more. So which part of information given to us we have not used so far? We have not used this information that it travels a distance of 300 feet, right? Okay, so what we can do is we can try to uh, integrate this expression for the velocity once more, because we know velocity is given as dx over dt, and see if we can use that, right? Okay, so what is our expression for velocity? Expression for velocity is v minus v0 equal to beta t cube over 3, right? Notice how I did not write vf over here, because we're looking for a generic velocity expression, right, at any given point of time, right? So this is at any given value of t, not necessarily just the final t. Okay, so v is equal to v0 plus beta t cube over 3, and v is also equal to dx over dt. So this is this. Now what I'll do is I will integrate it by bringing dt on the right hand side. This is changing from 0 to, let's say xf final, and this is from 0 to t. So what do we get? We get xf equal to v0t plus beta t to the power 4 over 12, right? That's what we get. Okay, so from this now, what do we know? Well, v0 is 0, so we don't have to worry about that, right? So we get rid of that. Now from this, we can compute, okay, this gives us another relationship. So xf is given as 300 feet to us, right? So 300 feet. Okay, we have to be unit consistent. So if we are doing everything in feet, then the miles per hour has to be converted into feet per second as well, right? If you're using USCS system, which seems to be the case over here. So now we have two equations, right? We have two equations and we have two unknowns. So beta is one unknown and t is the other unknown. We can divide 1 with 2 and solve for t from that. And then we can substitute for t in either 1 or 2 and get the beta from that.